Welcome to our lecture on probability. Probability is a very important part of the science of statistics. It is, in fact, the foundation of inferential statistics. So what is probability? Probability measures the likelihood an event will occur. Probabilities are expressed as a number between 0 and 1. 0 means an event is impossible. 1 means that it is certain. The probability that a man in his 70s will become a mother this year is 0, and the probability that he will die before his 150th birthday is 100%. Probabilities can be expressed as a percent, 10%, as a decimal, 0.1, or as odds, 1 to 9. Probability is about uncertainty. People have dealt with uncertainty for eons, which is why so many cultures have good luck charms. Probability is the scientific study of uncertainty. As Pierre-Simon Laplace wrote, the most important questions in life are, for the most part, really only problems of probability. Bertrand Russell, the 20th century English mathematician and philosopher, stated, "We cannot understand the scientific method without a previous investigation into the different kinds of probability." The physicist Richard P. Feynman noted, "Nature permits us to calculate only probabilities, yet science has not collapsed." This lecture has 9 objectives. 1. Review the origins of probability theory. 2. Cover Kolmogorov's 3 probability axioms. 3. Explain the 3 approaches to probability: classical, empirical, and subjective. 4. Explain the rules of probability. These rules include the special rule of addition, the general rule of addition, the special rule of multiplication, the general rule of multiplication, and the complement or subtraction rule. 5. Detail the rules of counting. These rules cover the multiplication formula, factorial numbers, combinations, and permutations. 6. Examine the Monty Hall paradox. 7. Review Bayes' theorem. 8. Highlight one of the tragic misuses of probability. 9. Quickly review Pascal's wager as an example of probability theory and decision theory. Let's review some important probability terms that you need to know. An experiment is a process that leads to one of several possible outcomes. An outcome is a possible result of an experiment. The sample space is the list of all possible outcomes. Mutually exclusive refers to experiments where only one of the possible outcomes can happen at the same time. Collectively exhaustive means that at least one of the possible outcomes must occur as a result of an experiment. Independent events do not affect the probability of another event occurring. Dependent events, on the other hand, depend on the outcome of a previous event. Joint probability is the likelihood that 2 or more events will happen at the same time. This Venn diagram on the right shows the joint probability of the events A and B. The joint probability is the area in purple. Let's turn to the origins of probability theory, which was developed in the 17th century to answer a question about a dice game. The heroes are 2 17th century French mathematicians, Blaise Pascal and Pierre de Fermat. When asked about a contemporary dice game, Pascal consulted de Fermat, and in doing so, these mathematicians are credited with codifying the foundations of probability theory. Probability was previously studied in Italy, India, China, and ancient Greece, but the principles of probability were not delineated until Pascal and de Fermat. The link between gambling and probability has been noted by scientists and mathematicians. Laplace wrote, "It is remarkable that a science that began by considering games of chance should itself be raised to the ranks of the most important subject of human knowledge. Mathematician Temple Bell remarked, "Games of chance are probably as old as the human desire to get something for nothing, but their mathematical implications were appreciated only after Fermat and Pascal reduced chance to law." What sparked Pascal's interest in probability? In 1654, Antoine Gombauld, a foppish writer who assumed the noble title of the Chevalier de Marais, asked Pascal to help solve a problem about a game of dice. Gombauld was an intellectual, not a gambler. The name Chevalier indicates nobility, but he was not a noble. This was part of his pen name. The question, is betting even money on rolling at least one double six in 24 rolls a smart bet? Conventional wisdom said it was, but was that true? Before we investigate this question, let's consider the sample space for rolling a pair of dice. Here is the sample space. There are 36 possible outcomes when we roll a pair of dice, as this image of black and red dice show. Only one outcome is a double six. The probability of rolling a double six is 1 over 36, or approximately 2.78%. To answer Gombauld's question, Pascal, who lived in Paris, exchanged letters with de Fermat, who lived in Toulouse. Only 7 of their letters exist today. Betting even money on rolling at least one double six in 24 rolls is not a smart bet. Let's find out why. The probability of not getting a double six on a single roll is 35 over 36, or approximately 97.24%. The probability of not getting a double six in 24 rolls is 0.9724 to the 24th power, or approximately 50.86%. The chance of getting a double six in 24 rolls of the dice is only 49.14%. A gambler betting on getting a double six at least once in 24 rolls will lose more than half the time. Clearly, this is not a smart bet. As this Excel workbook shows, the favorable odds of 50.55% for a double six requires at least 25 rolls of the dice. The game, however, is limited to 24 rolls, so the odds of winning are less than 50%. Clearly, the designers of this game must have had a very keen understanding of probability. Let's turn to André Kolmogov's 3 probability axioms. Remember, an axiom is a mathematical postulate that's taken to be true and serves as a starting point for further reasoning. Axiom 1. The probability of any event happening must be greater than or equal to 0. There are no negative probabilities. To repeat, the probability of 0 means that an event is impossible. Axiom 2. The highest probability of an event is 1 or 100%. Axiom 3. The probability of a series of events that cannot happen simultaneously can be found by adding the probability of each event. There are 3 approaches to probability. 1 classical, 2 empirical, 3 subjective. Classical probability is the first of the 2 objective approaches to probability. This form of probability is based on a priori probability, which means that the probability of an event is known before the event occurs. Examples of classical probability are the odds of winning the Powerball lottery and the probability of rolling a pair of dice and getting a 7. Empirical probability is the second objective approach to probability. Empirical probability is based on relative frequencies of an event. With empirical probability, the probabilities are found a posteriori, or after the event. Subjective probability is based on available information, hunches, and guesses. not objective facts like classical and empirical probability. Let's review classical probability. With classical probability, the probabilities of an event are known a priori, which is to say before the event. Classical probability applies to finding the odds of winning at dice, coin flips, or a lottery. Craps is a modern dice game in which the players bet on the outcomes of a roll of a pair of dice. Without getting into the details of this game, a roll of 2, 3, or 12 is called craps. The probability of 2, 3, or 12 equals the sum of the probabilities of getting a 2, 3, or 12. 1 over 36 plus 2 over 36 plus 1 over 36, or 4 over 36, or approximately 11.11%. The gambler's fallacy is closely related to classical probability. The gambler's fallacy is the notion that runs against the central premise of classical probability. It is the mistaken belief that the odds for something with a fixed probability depend on recent occurrences. The gambler believes that something is due, that his bad luck will change. This is a fallacy based on a misunderstanding of classical probability. The odds of gambling events do not change. Here is an example of the gambler's fallacy. Suppose we flip a fair coin 10 times and get all heads. Yes, this would be a very rare event, 50% to the 10th power. On the 11th flip, have the odds of a tail increased? No, the odds do not change. The probability of heads on the 11th flip remains 50%, as does the probability of a tail. Meyer Lansky, the late reputed organized crime leader, knew a few things about gambling. He was the boss of casinos in Las Vegas, Cuba, London, and the Bahamas. According to one biographer, Lansky said, "There is no such thing as a lucky gambler. There are just winners and losers. The winners are those who control the game. All the rest are suckers. The only man who wins is the boss." Let's turn to empirical probability. Empirical probability is a posteriori probability, or after the fact probability. This form of probability is based on the observed relative frequencies of an event. With empirical probability, the probability of an event is found by the times a desired outcome occurs over the number of observations. Here is an example of empirical probability. Suppose you're looking for a restaurant that offers gluten-free meals. You survey 10 restaurants and 7 say they have gluten-free items on their menu. The empirical probability is 70%, found by 7 over 10. Let's turn to the law of large numbers, which is associated with empirical probability. The law of large numbers was first articulated by John Venn, an English mathematician. Venn wrote, "Let's assume we toss a penny a great many times. The result of successive throws of the series seem to occur in utter disorder. The irregularity of a single instance diminishes when we take a large number, and at last seem for all practical purposes to disappear." With the law of large numbers, empirical probabilities converge with classical probabilities after a large number of events. Some scientists and mathematicians have informally tested the law of large numbers. In the 18th century, the French naturalist Comte de Buffon tossed a coin 4,040 times. Result, 2,048 heads, or a 50.69% probability. Around 1900, the English statistician Karl Pearson tossed a coin 24,000 times. The result, 12,012 heads, or a 50.05% probability. While a prisoner of war during World War II, mathematician John Couric tossed a coin 10,000 times. Result, 5,067 heads, or a 50.67% probability. And lastly, there is subjective probability. This form of probability is based on a person's knowledge, belief, judgment, hunches, or biases. Subjective probability is the heart and soul of Bayes' theorem and Bayesian statistics. We will review Bayes' theorem later in this lecture. We will now turn to the rules of probability. There are two addition rules. With addition rules, think OR. Only one of the possible events will happen. The special rule of addition is for mutually exclusive events, and the general rule of addition is for non-mutually exclusive events. There are two multiplication rules. With the multiplication rules, think AND. The events must happen together. The special rule of multiplication is for independent events. The general rule of multiplication is for dependent events. There is also a fifth rule called the complement or subtraction rule. This rule is used to find the probability of an event not happening by subtracting the probability that the event will happen from 1. Here is an example. As you will recall, the probability of rolling a pair of dice and getting a double 6 is 1 over 36, or approximately 2.78%. The probability of not rolling a double 6 is 100% minus 2.78%, or approximately 97.22%. Please note, the tilde is used to symbolize not. Here's a Venn diagram of the complement rule. The area of the gray box that surrounds the red dot is the probability of event A. The red dot is the probability of not A. Please note, events A and not A are mutually exclusive and collectively exhaustive. If we know the probability of A, we can find the probability of not A using the complement rule. We will now turn to the special rule of addition. The special rule of addition applies to the probability of two or more mutually exclusive events. The special rule of addition states that the probability of A or B or C equals the probability of A plus the probability of B plus the probability of C. The probability of rolling craps in a game of dice is the probability of rolling a 2, 3, or 12. 1 over 36 plus 2 over 36 plus 1 over 36 equals 4 over 36, or 11.11%. Gamblers playing craps will get a 2, 3, or 12 11.11% of the time. This is a Venn diagram of the special rule of addition. The three events are mutually exclusive because they do not overlap. We will now turn to the general rule of addition. The general rule of addition deals with the probability of two or more non-mutually exclusive events. Here is the formula for the general rule of addition for two non-mutually exclusive events. The probability of A or B equals the probability of A plus the probability of B minus the joint probability of A and B. To repeat, the probability of A and B is the joint probability, which is to say event A and event B happening at the same time. Here is a Venn diagram of the general rule of addition. The purple area is the joint probability of A and B. For our example of the general rule of probability, we will use a standard deck of playing cards. The deck of cards has 4 suits: hearts, clubs, diamonds, and spades. There are 13 cards in a suit: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Our question: what's the probability of selecting a spade or a king? Remember, the deck of cards has 52 cards with 13 spades and 4 kings. The outcomes are not mutually exclusive. There is the king of spades, hence the general rule of addition must be used. What is the probability of a king or a spade? Using the general rule of addition, the probability of a king plus the probability of a spade minus the probability of the king of spades. The answer: 4 over 52 plus 13 over 52 minus 1 over 52 equals 16 over 52, or 30.77%. We will now turn to the special rule of addition. This special rule of addition applies to two or more independent events occurring at the same time. Events are independent when the probability of event A, given that event B has happened, equals the probability of event A. The special rule of addition is often expressed with the word AND. The probability of event A and event B and event C equals the probability of event A times the probability of event B times the probability of event C. An example of the special rule of multiplication was Pascal-Fermat's solution to Gombold's question. Let's recap. The probability of throwing two sixes is 0.0278, or roughly 2.78%. The probability of not throwing two sixes is found using the complement rule. 1 minus 2.78% equals 97.22%. The probability of no double sixes in 24 rolls is found using the special rule of multiplication, multiplying 0.9722 by 0.9722 24 times. 0.9722 to the 24th power equals 0.5086, or 50.86% of the time. No double sixes will happen in 24 rolls of the dice. We will now turn to the general rule of multiplication. The general rule of multiplication applies to the probability of two or more dependent events. The general rule of multiplication is written as the probability of A and B equals the probability of A times the probability of B given that A has happened. P, open parenthesis, B, straight vertical line, A, close parenthesis, is read as the probability of B given that A has happened. Let's work through an example of the general rule of multiplication using a small bag of M&Ms purchased from a vending machine. What's the probability of selecting 3 M&Ms when the candy is not returned after selection? These events are dependent or conditional because the probabilities of selecting a red M&M change when you do not return the candy after it has been selected. We express this calculation as the probability of red on the first pick and red on the second pick and red on the third pick equals the probability of red on the first pick times the probability of red on the second pick given that red was selected on the first pick times red on the third pick given that red was selected on the second pick. The calculation 13 over 57 times 12 over 56 times 11 over 55. Note that the probabilities change for each pick because the selected candies are not returned to the bag. Converting the fractions to decimals, we get 0.2280 times 0.2143 times 0.2039, which equals 0.0098. There is a 0.98% chance of selecting 3 M&Ms when the selected candies are not returned to the bag. Putting it all together, the probability that Apple stock will increase in value next year is 70%, subjective probability. The probability that Microsoft stock will increase in value next year is 50%, also subjective probability. What's the probability the value of one or both stocks will increase? Assume the value of these stocks are independent. To solve this problem, use the special rule of multiplication 3 times. 1. The probability that Microsoft stock will increase in value, but not Apple stock. That probability is 0.15 or 15%. 2. The probability that Microsoft stock will not increase in value, but Apple stock will. That probability is 0.35 or 35%. 3. The probability that both Microsoft stock and Apple stock will increase in value. That probability is 0.35 or 35%. Note the use of the complement rule. Once these 3 probabilities are found, use the special rule of addition to add the 3 probabilities. The probability of at least one of these stocks increasing in value is 0.85 or 85%. Let's turn to the Monty Hall paradox. Monty Hall was the host of a TV game show called Let's Make a Deal. The Let's Make a Deal TV quiz show ran from 1963 to 1976. In 1999, the Monty Hall paradox was posed by Marilyn Vos Savant in her Ask Marilyn weekly column in Parade magazine. Savant is listed in the Guinness Book of World Records under the highest IQ from 1985 to 1989. The paradox is based on a game like the ones played on Let's Make a Deal. The game involves 3 doors and 3 prizes. Each door conceals a prize. Behind one door is a new car. There is a goat behind the other 2 doors. A lucky contestant is selected from the audience. The contestant picks one door and wins whatever is behind it. You are the contestant and you want the car, not a goat. You pick door A. It really does not matter which door you select. What's the probability of selecting the door with the car? You have a 1 in 3 chance of picking the door with the car. That is a 33.33% chance of winning. Monty opens a door you did not pick to show a goat. Now the game gets interesting. Monty asks, "Do you want to switch to the other door?" What should you do? Are the odds of winning now 50-50, as some scholars have suggested? Here is Vos Savant's correct solution. The odds of winning are not 50-50. Your chance of winning the card changes based on your decision about switching doors. By switching doors, your chance of winning the card jumps from 1 in 3 to 2 in 3. Praise for Vos Savant from computer scientist Judea Pearl. Her solution is astounding in its simplicity and more compelling than any I have seen in many textbooks. She made a list of the 3 possible arrangements of the doors and goats, along with the corresponding outcomes under the switch strategy and stay strategy. Here is Vos Savant's list. The switch strategy offers 2 out of 3 chances of winning, while the stay strategy only offers 1 chance out of 3. Vos Savant received over 10,000 abusive letters informing her that she was wrong. Here are just a few comments. You blew it, and you blew it big. You are utterly incorrect. You are the goat. One letter even suggested that she erred because she looks at math differently than a man. Let's turn to the rules of counting. There are 3 rules of counting. The first is the multiplication formula, which must not be confused with either the special or general rules of multiplication. The second is combinations, and the third is permutations. Both combinations and permutations use factorial numbers. Factorial numbers include an exclamation mark. The multiplication formula. If there are m ways of doing one thing and n ways of doing another thing, there are m times n ways of doing both. A car comes in 9 colors and 3 body styles. How many arrangements of colors and body styles are there? Easy. M times n equals 9 times 3 equals 27 arrangements. A car comes in 9 colors, 3 body styles, and 2 engines. How many arrangements of colors, body styles, and engines are there? M times n times O equals 9 times 3 times 2 equals 54 arrangements. How many 5-digit numeric codes are available? Answer: 10 to the 5th power. 10 times 10 times 10 times 10 times 10 equals 100,000. How many 5-digit numeric codes are available, assuming you cannot use the number 5? Answer: 9 to the 5th power. 9 times 9 times 9 times 9 times 9 equals 59,049. How many 5-digit numeric codes are available when no number can be repeated? The answer is 30,240, found by 10 times 9 times 8 times 7 times 6. How many 5-digit codes are available when you can use numbers and letters? There are 36 possibilities for each digit. the numbers 0 through 9, and the letters A through Z. Answer: 60,466,176, found by 36 to the 5th power. Factorial numbers express the way n elements can be ordered. Factorial numbers include an exclamation mark after the number. With factorial numbers, we multiply all whole numbers from our chosen number down to 1. 4 factorial equals 4 times 3 times 2 times 1, which equals 24. There are 24 ways to arrange 4 widgets. 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 120. There are 120 ways to arrange 5 widgets. Here are the values of factorial numbers from 0 factorial to 10 factorial. The Excel formula for factorial numbers is =, fact, and the number. Combinations express the number of ways to select R objects from a group of n objects when order doesn't matter. The combination of R things selected from n things, where R is the number of items selected and n is the number of objects, equals n factorial over R factorial times n minus R factorial. A circus has 5 elephants. How many ways can it select 2 elephants when order is unimportant? The combination of 2 things selected from 5 things equals 5 factorial over 2 factorial times 5 minus 2 factorial. 5 factorial equals 120. 2 factorial equals 2. And 5 minus 2 factorial equals 3 factorial, which is 6. And 2 times 6 equals 12. 120 over 12 equals 10. There are 10 ways to select 2 things from 5 when order does not matter. Here are the 10 combinations of 2 elephants selected from 5. Excel's combin function quickly calculates combinations. This function has 2 arguments. The first is the total number of objects. The second is the number of objects to be selected. Permutations express the number of ways to select R objects from a group of n objects when order matters. The permutation of R things selected from n things, where R is the number of items selected and n is the number of objects, equals n factorial over n minus R factorial. A circus has 5 elephants. How many ways can it select 2 elephants when order matters? The permutation of 2 things selected from 5 things equals 5 factorial over 5 minus 2 factorial. 5 factorial equals 120. 5 minus 2 factorial equals 6. 120 over 6 equals 20. There are 20 ways to select 2 things from 5 things when order matters. Here are the 20 permutations of 2 elephants selected from 5 elephants. Excel's permute function calculates permutations quickly. This function has 2 arguments. The first is the total number of items. The second is the number of items to be selected. Let's look at the likelihood of winning the Powerball lottery. Here are the Powerball rules. Select 5 numbers from 1 to 69. The order of the selection does not matter. Select a Powerball number from 1 to 26. There are 2 steps to calculate the probability of winning the grand prize by getting all 6 numbers. Step 1, use the combinations formula. Step 2, use the special rule of multiplication. The combination of 1 item selected from 26 is 26. The combination of 5 items selected from 69 is 11,238,513. Now use the special rule of multiplication to calculate the number of possible outcomes of 26 times 11,238,513, which equals 292,201,338. Each Powerball ticket has a 1 in 292,201,338 338 chance of winning. Let's turn to Bayes' theorem. Bayes' theorem revises predictions as more information is acquired because, in the mangled statement of the great Yogi Berra, it's tough to make predictions, especially about the future. The history of Bayes' theorem. Thomas Bayes was an 18th century statistician, philosopher, and Presbyterian minister. His theorem is concerned with how probabilities change when new data becomes available. After Bayes' death, his friend Richard Price, a philosopher and nonconformist minister, found this work while going through his friend's papers. Price presented Bayes' idea to the Royal Society. Then Bayes' work was ignored. Years later, Laplace refined Bayes' idea and named this theorem after Reverend Bayes. There are two important Bayes' theorem terms. The first is prior probability. This is the initial probability based on available information or guesses. Prior probability is often based on subjective probability. The second term is posterior probability. Posterior probability is the revised probability based on additional information. Here is the basic Bayes' theorem formula. The probability of event A1 given that B has occurred equals the conditional probability of B given that A1 has occurred times the initial probability of event A1 over the conditional probability of B given that A1 has occurred times the initial probability of A1 plus the conditional probability of B given that B2 occurred times the initial probability of A2. Let's use Bayes' theorem to solve the Monty Hall problem. Here are the prior probabilities for door A, B, and C. The prior probability that any of the three doors conceals the car is 33.33%. The prior probability that the car will not be behind the door is 66.67%. Let's say you select door A. Hall responds by opening either door B or C. He never opens the door hiding the car or the door a contestant picked. Let's say he opens door B and a goat is revealed. The car, therefore, could be behind either door A, which you picked, or door C. Hall asks, "Do you want to switch to door C?" You now need to calculate the conditional probabilities. When Hall opened door B, he was giving you more information that alters the prior probabilities. Three more calculations are needed. 1. The probability that Hall opens door B if the car is behind door A. The probability that Hall opens door B if the car is behind door A equals 50%. You now need to calculate the posterior probability. 2. The probability that Hall opens door B if the car is behind door B. If the car were behind door B, Hall would not open this door. This probability therefore equals 0, and the posterior probability would be 0. 3. The probability that Hall opens door B if the car is behind door C. Let's explain. He cannot open door A because that is the door the contestant selected. So if the car were behind door C, there is a 100% probability that he would open door B, which Hall knows has one of the two goats. We can now calculate the posterior probability of the goat being behind door C. The stay strategy, sticking with door A. The probability that the car is behind door A when Hall opened door B is 33.33%. Nothing is gained from the stay strategy. Switching to door C doubles the probability of winning the car. The probability of the car being behind door C when Hall opens door B jumps to 66.67%. Switching doors makes sense because it doubles the probability of winning the car. The probability of winning the car goes from 33.33% to 66.67%. Let's turn to the sad tale of Sally Clark and the misuse of probability. Meet Sally Clark, wife, mother, and lawyer. She was born in 1964 in the United Kingdom. Her father was a decorated senior police officer. The first tragedy, death of an 11-week-old son. Christopher died in his Moses basket at the end of 1996. The coroner rules that this death was from natural causes. The second tragedy, death of a second infant son. Harry died in his bouncy chair in January 1998. The coroner also ruled that this death was from natural causes. Then the coroner changed the death report to smothering. July 1998, Ms. Clark was charged with murdering both babies. Meet the state's expert witness, Dr. Samuel Roy Meadow, author of the ABC of Child Abuse. Meadow's Law: 1 sudden infant death is a tragedy, 2 is suspicious, and 3 is murder until proven otherwise. Meadow hypothesized that 40% of crib deaths are murders. At Clark's trial, Meadow applied the special rule of multiplication. He argued that the probability of 1 sudden infant death syndrome is 1 in 8,854, or 0.00011,724. The probability of 2 SIDS deaths is 8,544 times 8,544, or about 1 in 73 million. In November 1999, Clark was convicted based on Dr. Meadow's expert testimony. But was Dr. Meadow's testimony sound? No, says the Royal Statistical Society. The Society raised serious concerns with how Dr. Meadow used statistics. The Royal Statistical Society raised 2 objections. The approach is, in general, statistically invalid. It would only be valid if SIDS cases rose independently within families, an assumption that would need to be justified empirically. Not only was no such empirical justification provided in the case, but there is very strong a priori reasons for supposing that this assumption will be false. There may be unknown genetic or environmental factors that predispose families to SIDS, so that a second case within a family becomes much more likely. The Society's second point: the well-publicized figure of 1 in 73 million thus has no statistical basis. It cannot reasonably be justified as a ballpark figure because the error involved is likely to be very large and in one particular direction. The true frequency of families with 2 cases of SIDS may be very much less incriminating than the figure presented to the jury at the trial. What happened to Ms. Clark? During the second appeal, the court declared that Meadow's numbers were subject to qualifications that were never presented to the jury. In January 2003, Clark's conviction was overturned and she was freed from prison. The Attorney General ordered reviews of hundreds of similar cases, and 2 convicts were freed. In March 2007, Clark died from acute alcohol intoxication. Let's turn to Pascal's wager, applying decision theory to the belief in God. In addition to being a mathematician, Pascal was very religious. He developed an argument for living a pious life called Pascal's wager. This argument is akin to modern decision theory. Pascal was a Catholic. He believed in heaven and hell. Pascal's wager states that believing in God and living a pious life is a smart bet. Here is the 2x2 matrix Pascal sets up. There are 2 wagers. 1, the wager for the existence of God, and 2, the wager against the existence of God. There are 2 possible outcomes to this bet. 1, God exists, and 2, God does not exist. If you wager for God and God exists, you will go to heaven and spend eternity in paradise. But if you wager against God, you'll be doomed to eternal torment in hell. Of course, there is a chance that God does not exist. In such an event, there is no gain or loss for either bet. Given the high stakes, Pascal argues that betting on God is the only bet that makes sense. Pascal also argued that those who believe in God have better lives. Except where otherwise noted, Clear-Sighted Statistics is licensed under Creative Commons license. You are free to share derivatives of this work for non-commercial purposes only. Please attribute this work to Edward Volchak. You can access Clear-Sighted Statistics for free, along with its Excel and PowerPoint files on the CUNY Commons. The URL is https://cuny.manifoldapp.org/projects/clear-sighted-statistics.